Can you tell me how to get rid of this stupid bar? Whatever you can get rid of. Yeah.
Like minimize.
Yeah. Just need all these things minimized.
I think it's a minimal that you can get.
Okay, this is what it is. Okay, fine.
You can do it more? Oh. Okay, let me try that.
Yeah.
Wow, thank you so much. This one?
New information.
Okay.
Yeah.
No, I don't want to know this. Therefore, I'll always ask someone to help me. Yeah. Okay, let's get started. Okay, so today this is lecture 5A, and this is going to be on essentially stuff from classical robotics that everybody should know. Okay, and I'm going to divide this up into 3 segments: robot dynamics, control, and motion planning. So people who have taken a full-fledged classical robotics class should know all this. Others may not, but I think that I need to do a review to bring everybody up to the same place. Okay, so let's see. Okay, so the 3 topics are robot dynamics, robot control, robot motion planning. Very straightforward. Okay, let's start with dynamics. So first of all, going back some lectures ago, maybe in the second lecture, we talked about robot kinematics. So this is essentially about the geometry of the system. So you have a frame at the base of the robot or somewhere in the room, which is called the S frame. And then there is a B frame, which is the body frame, which is somewhere on the robot. And what we know is the geometry. So we know the lengths of every link. And we have joint angles. And with this, we can calculate the configuration at, for example, the end effector. And the solution was that it is essentially a series of exponentials of screws that we compose them together, and that's how we get the final configuration. And again, we did the big story last time. So the product of exponentials is a nice, elegant way of stating this. It is derived from what are called Lie groups and Lie theory. But there is a simple version of it, which is just for rotations, which is exponentials of skew symmetric matrices represent rotations, and then you can compose them. And there's a generalization where both rotations and translations are being considered. And that's where you need to consider the so-called screw motion. Okay, how do we make all this practical? This is made practical through the URDF. So we describe every robot using this URDF, and the robot manufacturer is supposed to supply to you the URDF. So if you look on the lower left, that's the kinematics. What is it telling you? You can read it. Name joint 2, type revolute. So therefore, that's a revolute joint. There's a parent link, a parent-child link, origin, axis, length. So this is basically telling you about the geometry, like how long are the links and so forth, right? And then if there are joint limits in terms of what angles can be achieved or not achieved. Okay, there's a second part on the right, which is called the link element, and it refers to inertial properties. So inertia here as in inertia of movement. So basically we're talking about physics. F equals ma, torque equals I times omega. That's what is involved here. And if you notice what's being described there, the mass, so we're probably the mass of the robot link in kilograms or whatever. Then there is the inertia, which is in IXX, IXY. So these are different axes about which you compute the moments of inertia. So all of that is specified, and this is the physics of the robot. So we specified the geometry of the robot and the physics of the robot in this URDF format. And then what we have to do is to figure out the dynamics. Dynamics here refers to forces and torques and movement in various ways. And there are two problems here. One is what's called the forward dynamics problem. So the forward dynamics problem is that you are given theta. Theta here is a vector. This corresponds to all the joint angles. There's theta dot, which is how are all the joint angles changing. There's tau. Tau here is a vector corresponding to the torques applied at every joint. So basically you have some electric motors which are applying torques at every joint. So this is the input, and then the output is theta double dot, which is how are the joint angles accelerating, because physics is about accelerations. F equals ma. A means acceleration, right? So that's the forward dynamics problem. We are in a certain configuration. We apply some forces or torques. What will happen next? What will be the acceleration? And then you can kind of integrate from that, right? So that you have a short moment in time delta t, you figure out the new configuration, you continue. So that's a forward problem. There is the inverse dynamics problem. So the inverse dynamics problem is that what do you control? You control all your electric motors which are rotating all the joints. So that's the tau, right? Tau here is a vector of torques. So that's what you want to control. And what's the input? Input is whatever you want in terms of desired configuration, desired rate of change of configuration, and so on. So the input is theta, theta dot, theta double dot. So this is a very well-defined problem. And essentially, nice ways of solving it were worked out back in the 70s and 80s and 90s. So it's all, there's a solved problem. You don't need to worry about it. It's all worked out. It's there in the libraries. But I'm going to give you the 5-minute version so that you have some intuition of what's going on underneath the hood. And again, for dynamics, there are classic ways of doing it. I mean, F equals ma, the Newton method, which you can integrate in time. This is what you learned in high school or whatever, freshman physics or whatever. And then there's a fancier way, which is the Lagrangian dynamics. The difference between them is essentially when you have multiple degrees of freedom and the motion is constrained in some way, then the Lagrangian formulation is more convenient because it's in terms of the true degrees of freedom of the system. Okay, so I'm going to do like this very cartoon version of this so that you have a feeling of what it's about and don't expect to really understand this properly. To understand this properly, you should take 106A, which is the class Shankar Shastri teaches. So that's the answer. So, but I want I feel that there's nothing you should learn as a black box. You should have some intuition. So I want to give you some intuition. So this is a simple 2-link robot. You have this first link, and then there is this thing which is connected to it. So there is this mass M1 is the first link, and mass M2 is the second link, and then you can rotate the first link. So that has a revolute joint at the base here. Okay, and then the second joint is a prismatic joint, so you can move it, translate it. Okay, so you don't want to actually use this robot. This is a very simple robot to just illustrate concepts. So what you're supposed to do in the Lagrangian formulation is that you're supposed to figure out the potential energy and the kinetic energy and take the difference of the two. So the kinetic energy minus the potential energy. And this is sometimes called the action. Yeah. Okay. And now, so so again, to give the flavors of the terms, the first term. So what's the first term? M1 G Y1. So this is potential energy. So it's basically your mgh, right? Mass times the acceleration due to gravity times the height. That's what, again, you're supposed to have learned this in high school. Okay, so now that height here is in the y, so there's a xy coordinate system and the y is the height. So you calculate the height and it's going to be L1 times the sine of theta 1. Okay. Similarly for the second joint. What's the kinetic energy? Kinetic energy is basically half mv squared, right? So you have to figure out what is the velocity, which for the first joint is going to be in terms of x1 dot squared plus y1 dot squared. And then there is this second term which has to do with this rotational inertia, so moment of inertia I, and then theta 1 dot, which is the angular velocity. Okay, I've just waved this in front of you, and I'm not going to continue in detail of the rest of the calculation. But if you are curious, I've got this reference on the slide, which is Feynman lectures. When I was a kid, I read this chapter on the principle of least action. It is one of the most beautiful expositions of this principle, which is underlying Lagrangian mechanics. Okay, but you can find it in Feynman lectures, and you can actually find this lecture on YouTube. I mean, I had to read it from a book anyway. So, okay. And then blah, blah, blah. So, okay, now you do a lot of algebra, and at the end you get this equation, which is at the top. So I think we can look at the abstracted form of this equation. So let's just understand what the terms are. Tau is a vector. So this corresponds to the torques applied at each of the joints. So if you have two joints, so there might be two of these, right? What is m of theta? M of theta is some matrix. The m is supposed to tell you that it's about masses. So it's the mass in some form, right? It's the inertia part. What is theta double dot? Well, that's the second order centripetal forces and Coriolis forces. And so that's indicated in the second column vector. And then there is this g of theta. The g here stands for gravity. So this is the gravitational part. So you can see the terms g showing up in each of these. Again, the derivation here is following standard stuff which any physicist in 1800 could derive. Right? He would not have used vector matrix notation, but it's basically that. Okay, so we can work all this out, and okay. But now let's just just act like computer scientists. We've got an abstraction on top. So the abstraction on top is that there is this kind of an equation, which you can write down in 4 different forms, but it's the same equation. So one is the torque equals m these are matrices and vectors, just remember that, plus this h. This h is can be split into 2 terms, one part which is kind of this velocity product terms, one part which is due to gravity. Then this can be written in other ways, blah, blah, blah. Okay, it's just these are different formats in which we write down the basic physics of the situation. And then there is this term, this last term, which is somewhat interesting and now relevant for robotics. There is this Jacobian transpose of theta times f tip. What is that? So if you are trying to apply a force at the tip of the robot, so this you might want to do, right? Suppose what you are trying to do is with your robot tip, you're trying to apply some force to the wall, or you're trying to screw something in or push something, you're applying a force, right? So there's an external force that you want to be output from the system. So that's that term. And then the Jacobian is going to do the appropriate transformation in the system. So the intuition is quite easy and clear, and the mumbo jumbo can be worked out by other people or by some computer algebra system. Okay, next. So that's my topic 1. So you can spend a few weeks and understand this properly, or you can just take it that at the end you'll get a system of equations of this type. Trust me. Okay. The second part of this lecture is about control. And because we are now getting into the game that we need to do something. So we are going to apply some torques at the joints with the goal of achieving a certain movement of the end tip of the robot, or some application of forces, or both. And I'm going to give you examples where for different manipulation tasks, you need to either apply do movement control or force control. Let's give one easy example. Suppose you want to write on the board. Then the marker that you're using, the tip of the marker needs to move on a certain trajectory. So that's movement control. But then there is a force which you apply into the whiteboard, which you want to be a little bit, but not too much, right? So that's the force control. So once you have force and movement control, then it's called hybrid control because you're controlling both. So we want to understand control. Now, now there is a schism based on whether you're an E undergrad or a CS undergrad. So every E undergrad should have taken a class on control. Okay. Very likely every CS undergrad has not taken a class on control. Okay. And the way you encounter control is probably through reinforcement learning. And reinforcement learning is very fancy mumbo jumbo. In principle, you should never learn reinforcement learning without having studied control first. But sadly, that's not the way the educational system works. So it is my duty to make up for this gap in your education. Okay. Can I just take a poll, by the way? How many people in this room have not taken a control class? Okay. So I think it's like maybe 1/4, 1/3. So it justifies me teaching it. Even for the people who have done control, you might, I'm hoping you've forgotten enough of it that this class offers some value. So I've got this super baby example, but this is essential to understand. With this, you can understand the intuition of control. So the problem we're going to study is like this very tiny, easy problem, but it illustrates what control is about. So the problem is that of driving your car and cruise control. So what we are doing is we are driving a car, and this is an old-fashioned car. There are no computers involved. It's like you pressing on the accelerator. So this is called the throttle. So there's an angle, and every time you press down by 1 degree, the speed of the car goes up in some way. Okay, so that's so the controller here is like the human, or it could be some computer program. What's the control variable? The throttle. So the throttle is this, how much you press down on the accelerator, so the angle. Okay, and then there is an actuator. Actuator is the terminology. In this case, it stands for the engine, right? The internal combustion engine, the electric motor, whatever. Okay, and then there is this, the auto body. I mean, the 2,000-pound mass, which is your car. And then this is affected by the road surface, which, let's say, you don't know. The road could be flat, the road could be sloping up, the road could be sloping down, right? And you don't know exactly what it is, but it's going to exert some disturbance on the system. Okay, and then as a result, you get an actual speed for a certain setting of the accelerator, right? And then, of course, you have a speedometer, so you can measure the speed. So this is a very simple scenario. So, but this is more interesting. I mean, when control is introduced, the first example is that of a thermostat, but this should be the second example. So I'm taking just the second example. Okay, so now let's convert it into math. And the mathematical model is shown here. So there is some control which is in degrees. So degrees of angle on your accelerator. Then there is some output speed. And our simple model here is a 1 degree change in throttle angle causes your speed to go up by 10 miles per hour. Simple, just a model. And then you have the effect of the unknown environment. And the effect of the unknown environment is that the slope of the road surface. So if a 1% change in grade causes a speed change by 5 miles per hour. So if you are going uphill at a slope of 1 degree, your speed will be reduced by 5 mph. If you're going downhill, it'll go up by 5 mph. Okay. So there are gross simplifications about the dynamics here, which is fine. This is just a simple model. Okay, so far so good. Okay, now how do we control this car? Okay, so what the simple-minded way is what open loop control or feed forward control. So what would you do? So you have this variable R, which is you get to control the thing here, right? So what you do is you want a certain speed, so you just press the accelerator by that amount, right? Okay, so you get your y equals, so the variables here are u is the control, that's a standard term symbol used for control. It goes back, I believe, to maybe Alyosha knows this. The word control in Russian begins with something with a u. Have you? I have no idea. Okay. So anyway, that's what somebody told me, but I need to verify this. Okay. So okay, so you can work out and then there is the open loop approach, which is that you press the accelerator by the amount that you need to in order to get the right speed. That model will do the right thing, except for the fact that there is this disturbance, which is the fact that the road that you're going on has some slope. And we've got a little model here of that phenomenon, which is that there is so essentially there is this the effect of so there's y. Y equals 10 of u minus 0.5 w. Okay, so this is essentially saying the effect of the accelerator, which is the control u, and then there's the effect of the slope, right? And then and then this is this 0.1 r is what we worked out because we have this rule that we had here. There's 1 degree change causes a speed change by 10 miles per hour. So because of that, we did that. We did do this 0.1 thing. Okay, minus 0.5 w. And then if you work this out, it comes out to be r minus 5 w. Okay, so let me explain all of this. Y is the actual speed. R is the reference speed. So this is standard terminology from control. So the reference speed might be 50 miles per hour or whatever, right? So and then minus 5 w. So what this is saying is that in open loop control, if there is no disturbance, there is no noise, there is no road slope, it's flat, then the effect of this 5 w is 0, and y is equal to r. So that means that the car goes at the desired speed, and it's simple. Open loop control is correct. There's no problem. Okay. Now, if there is actually a slope, okay, then you're going to get an error, right? So if there's a slope of 0.1 whatever the slope w, you're going to be off as a result of that. And this is the problem with feed-forward control, that there will be some unknown aspects of the environment because of which you will screw up. Okay. Now, what's the idea of closed loop control? Closed loop control is that what you do is you look at your speedometer right? So you look at the speedometer and you look at what is your actual speed, and then you have in your mind the desired speed, and you measure the error. Okay, so this is the key concept of control. There is a desired speed, there is the actual speed, you make a measurement. You make a measurement, the difference is, we call the error. Now what do? Basically, what you want to do is to drive the error to 0. So it's really the spirit of gradient descent. You have some error, you want to drive it to 0. So what you will do is you will apply some correction which is proportional to the error. That has to be the spirit of it. Apply some correction which is proportional to the error. Okay. So we can work out the math of this. So it's very important here that you have a way of measuring the output, and you have your desired output. So the desired output is R, the actual output is Y, right? So, and the control is, so you've got this block here, it's got this R, and then there is this essentially this differencing happening here between R and Y, because you have the ability to measure the output. Okay, and then the control is, so this R minus Y is an error, right? And what you do is you say, I don't like the error, so I'm going to apply a control. And let's say I do 10 times that. That's the control I apply. Okay, and now we can write down our equation. So there is this equation that we already had, U minus 0.5 W. This was in the previous slide, right? That's just the straightforward thing. Now, in this U, there is the Y, and then there is a separate equation for Y. So I can plug in, so basically I can eliminate the variables from this, and I can eliminate the U. So Y equals 10, U minus 0.5 W, and this U is 10R minus 10Y minus 0.5 W, right? So this is giving me 100R minus 100Y minus 5W. Okay, and then I can take this 100Y here and make it 101Y, right? Which means Y equals 100 upon 101R minus 5 upon 101W. Okay, so that's my, so now I have 100 upon 101 is 0.99, 5 upon 101 is approximately 0.05. So the net result is Y equals 0.99 R minus 0.05 W. Okay, so notice what's so cool about this. So what's the effect of the disturbance? The effect of the disturbance previously was 5 W, and now it's become 0.05 W. So the effect of the road grade, upslope, downslope, is severely diminished. It's been diminished by 100x. Okay, and you paid a little penalty for it, which is that the Y is 0.99 R. So you didn't get exactly your 55 miles per hour, but 54.1 or 54.2. So you lost a little bit in this, so suppose there was no grade, right? The road was flat, you would still pay that penalty. So so there is a steady state error here. You're not achieving Y equals R, you're achieving 0.99 R, but that's like a small loss. And the big thing is you've got rid of the consequence of the disturbance, which is W, and the disturbance has been diminished by a factor of 100. This is the beauty of control. And did you need to know what is the effect of the road? No. This is your model-free system to kingdom come. You know, we talk about model-free reinforcement learning and model-based reinforcement learning. This is totally model-free. You do not need to know anything about the system. How well your system works in practice will depend on the model, but all you did as an engineer was to say, measure the error, and then apply a correction which is proportional to this. Alyosha.
On the flat surface, what's the intuition? Why are you paying the penalty?
Because
error should always be zero.
No, because essentially the correction here is based on error.
Right.
So you have to have an error in order to have a correction. Otherwise, you don't. So there is a way to fix this.
Zero if it's on flat surface.
No, the error is not zero here with this algebra, right? So you want it ideally to be zero, and there is a way to achieve it, and I'll get to that. Okay, no, so that's a desirable point, that you want it to be zero, and how do we achieve that? I will come to that. But this simple-minded scheme doesn't achieve it. Okay, but this simple-minded scheme achieves the goal of the effect of the disturbance is reduced by a factor of 100. And with nothing, with no knowledge really, you do not need to know much about anything. You do not need to know about the noise. You do not need to have a system like that. The effect of the W it can be unknown to you. You don't know how much it is. You do not need to know the grade. You do not need to know how much it messes up your system. All that it doesn't matter, right? How effective it is depends on that. But you as a designer don't have to do this. You as a designer just had to think of this number 10. I'm going to take this error and then I'll feed 10 times of this. Yeah.
Wait, does this system still assume that you're using the same logic as the like feed forward controller in order to calculate like the input?
No, I mean, the logic is everything is there on this slide. There's no feed forward here. I mean, again, we will come to fancier schemes which have both a feed forward and a feed back component, and we want them for any complicated scheme. This is like the most baby version, and I wanted to do this baby version because if you are a computer scientist and have never taken a controls class, this is like your introduction to control. Yeah.
The 10, the flat ground constant.
Yeah.
Do you still need it here? Because it seems like with the error, you should be able to.
No, you don't need to know about it.
Okay.
That's the point.
Okay.
You don't need to know about it because all you need to know is there is an error. The designer of the control system needs to know nothing about the system. This is the beauty. It is totally model free. I mean, it's like nothing. All you need to do is measure the error and then just act on trying to reduce it. It's like the beauty of gradient descent. It's actually Ben Recht has a post on connecting gradient descent and PID control in exactly this way. Okay. Now I'll do the slightly fancier version. Yeah, question.
It's like reason it is able to be model-free is because the sensing and the control are in the same
Space.
same space.
Yeah.
Then
Then you need to take a control theory class. So no, so the point is in the fancier versions, we deal with all that. So like, yeah, as I told you, I'm giving you the most basic version just to give you an intuition. Okay. Okay. Now, what do people do in practice? So what I described, the next version of this is what's called a PID controller. So PID, what do these three letters stand for? P is proportional. Actually, what we did so far was a P controller because it was you measure the error and the control is proportional to the error. So in this case, it was 10 times the error, right? So that's it. The proportion P is for proportional to the error. And then I is the integral of the error. So you can look at your past history and you just observe the error and you keep integrating that, keep a sum of the error. And that would deal with this problem of the so-called steady state error. Because if you are not going at the right speed and you are slightly off, this integral term will keep accumulating. And then to drive that to zero, you will do the right thing. Then there is a term called D, which if I is integral, then what should D be? Derivative. So then you have a derivative term. And the idea there is that if the derivative is positive and high, that means that the error is about to increase even more, which means you better put in even more control. That's it. So the idea of control is three numbers, okay? The P term, the I term, and the D term, which are indicated by these constants, K sub P, K sub I, K sub D. That you take a Kp times the error, Ki times the integral of the error, Kd times the derivative of the error, and you feed that in. That's it. And this is called a PID controller. And the claim is that 95% of controllers used in the real world are PID controllers. So again, my control theory colleagues have to teach you for 1 semester or 2 semesters, but actually I've just explained to you the PID controller in 10 minutes. And this is what is used 95%. This 95% number is probably made up, but I've seen this from control theorists. Yeah.
since we are observing theta again, why do we need the integral? Like,
No, well, we are observing the error from the past. So you use the history. Yeah. So so this is okay. So now what could go wrong? Okay, let's think about what could go wrong here. What could go wrong? So the natural answer is just keep increasing the gain. If these Ks are sometimes called gains. So if you make the Ks larger, then actually it does a better job in terms of reducing the error. But no, it doesn't go on forever because at some point you get instability. So the control loop, things go unstable. And understanding that was actually the beginnings of control theory. So there was a lot of work on these kinds of amplifiers and controls done by Bell Labs in the 1920s and 30s because there was a signal to be sent across the continent for long distance phone calls and you needed to amplify it. But if you amplify too much, then you get into trouble. I mean, we hear that all the time when you have a speaker and you get that signal. That's a example of this instability, right? So there can be, and so the control theory people essentially worry about this. So they think about this dynamical system and they want it to converge to a point and not go off in crazy ways. And anyway, that's a lot of the seriousness is about that. This is model-free control. Of course, control, there are variations of control. There are model-based control. So if you look at the areas like optimal control, those are model-based. So you have some model of the dynamics of the system. So something like x dot equals ax plus bu. So here you know the A and B. This is the dynamics of the system, how it's evolving. And then somebody was asking me about observation. So the observation can be something else, y, which is related to the state of the system. So x here stands for state and u is the control. X and u are vectors, A and B are matrices, and so on. And this is the linear version. And then with this, then you can have a cost function, which is you want to have minimize error, not use up too much control energy, and so on. And then you can work out the math. And that's model-based control. So control has both model-based and model-free versions, as we do in reinforcement learning. So reinforcement learning, you should think of as starting from this base of control and then getting fancier. So the Markov decision processes were defined in the late 50s by Bellman. And control theory had existed for 100 years before that. There is the first theoretical paper on controls was written by James Clerk Maxwell or Maxwell's equations. He wrote a paper on it in like 1870s. And then in the 1920s and 30s, there was a lot of use of this for like in electronics and so on. So this is an old venerable field. Okay. Any questions? Yeah.
What's the difference between knowing the arm dynamics there and knowing the A, B, and C here?
So here we don't know the arm dynamics. There is some unknown arm dynamics, which so basically the controller can operate without knowing the arm dynamics. How effective it is will depend on the arm dynamics. I mean, so what, in fact, then there is a practical problem of how do you tune these controls? How do you set these, right? So they have to hack around. And there were in the old days various heuristics for tuning this. And I will tell you how we will deal with it now, because actually in practical robotic systems now we still have to deal with these controllers, because the lowest level controllers, the ones which control the motors at the joints, are actually PID controllers. So in fact, the setting of these constraints can be done by a higher level. So your higher level reinforcement learning algorithm can, among its output, produce the right choices of these constraint scale. So that can be the output of your RL policy. Okay. So now a little bit to connect just terminology. So this is when you apply these controllers, the error doesn't immediately go to zero. There is can be some overshoot and undershoot, and this is all standard terminology from the control community. There is this final error, which is called the steady state error, and some amount of time, which is called settling time. And if you do an undergraduate class in control, you'll have to write homeworks on all this stuff. And I had to do this in 1978. Okay. This is material from like that.
Nothing changed.
This part, no. The PID control is still good. I mean, your robot has them. And I mean, I studied it in 78, but this was known in the 1930s, right? Even this stuff, this x dot equals ax plus, this is around 1960. So this is very old, respectable field, which people should really know more about than they do. Okay. Okay, so now let's go to, go back to robotics. So with this little intro to control, let's go back to robotics. So this is how the block diagram is for for a robot that we might have in the lab upstairs. So there is a desired behavior controller. So the controller, then there's some amplifiers, actuators, and transmission. These might refer to some electrical motors. Then the motor will produce a torque. There's a dynamics of the arm and environment. Then you measure something. It all seems reasonable. All these diagrams with boxes and arrows, they all kind of make sense, and so does this one. Okay. The observation I would like to make here is that control systems often are hierarchical. And this is like a general bit of thinking about planning and control. So suppose I'll use the most cliched example. I want to go from here to Boston. How am I going to do that? So there is a high level planning stage that, okay, I go to SFO, I take a plane, then I do something in Boston. Well, then how do I get to SFO? Well, there is a stage which requires taking an Uber. Then before that, there is a stage which requires going from here to the front door of this building. Before that, there is a stage where I'm actually moving all the muscles of my legs, right? So control in any complex problem there's hierarchies, which which are important, but it's a bit of a mystery as to how to have them emerge automatically. Most of the RL literature tries to deal with this, but the solutions are really not quite there. Usually the solutions are designed. I mean, like I'm imposing this hierarchy here. So often in robot control, this hierarchy is imposed. So the lowest level of the hierarchy here is that there is my electrical motor, and I'm giving it some signal in terms of current, and then it is moving, and you have to, and if it's not moving at the right speed or it hasn't moved to the right position, you need to do something. So that kind of that low level controller is very typically a PID controller. Okay. And then there is a higher level controller which is deciding what are the right joint angles to try to strive towards. So that low level controller often has to work very fast. So it's like typically operating at 1000 hertz. Whereas your high level controller might be, some transformer or neural network which is operating at, 20 hertz. So the lower level controllers are always much faster. Okay. Does that make sense? Yeah. And this is, so what we do is we often abstract away the lower level stuff. In the lower level controller, we just say, okay, we trust the motor supplier or the robot manufacturer, and that the low level controllers will do sensible things. Hopefully they give you access to it. And typically the way you want access is because there'll be a low level PID controller. So you want to be able to tweak those Ks, the K sub P, the K sub I, K sub D. You need to be able to tweak those. So far, so good. Okay, now let's go back to robotics. And now I want to give you some examples of these, just some terminology here first. Motion control, force control, hybrid motion, force control, impedance control. So let's take examples. So these are all examples of actions that we might want our robot to perform. And some of these involve motion control. Some of them involve force control. Some of them involve a mixture of motion control and force control. So, so let's say polishing with a polishing wheel. Okay. Okay. So you're trying to remove some material, right? So what's key is that you have to apply force. So it's primarily about that force, right? Erasing a whiteboard, I gave you that example. So you need to be moving on the surface of the board. So therefore there has to be motion. If you don't move, that means there has to be motion. And then there has to be some lateral force applied, right? Some tangential force. Spray painting. This one, you don't care about forces. It's all about movement, right? And so on. Okay, back massage. Presumably this is, you have to move along the back of the person and you have to apply a force. So it's hybrid. So anyway, the main value here is to say that different tasks that we have for robots to do, they will involve a combination of movement, how the end effector moves, and forces to be applied to, and this is more or less trivial, right? Because if you want to change the environment, you have to apply forces. That is the only way to change the world. That's what Newton told us, right? Okay. Okay, so now I'm going to go through another little bit of cartoon math, basically. So I'm going to now take like the simple joint here. So this is like a revolute joint. It has mass m, and it is at angle theta, and I'm trying to rotate it from one position to another. And now let's try to design a control law to achieve some desired rotation. So what does the math say? So in this case, the equation for the dynamics, it follows that same pattern that we did earlier in the lecture. It's that same pattern with those different terms corresponding to the mass term, the velocity terms, the gravity term. But the yeah, because it's super simple. Yeah. So here we have essentially the torque is super simple. It's like there is a gravity term, there's a viscosity term, there's a mass acceleration term. Anyway, again, the details do not matter. You should just know that somebody can work all this out because we are living 200 years after Newton and Lagrange. Okay. So, okay. So what you want to do is now let's put in the control theory stuff here. So the torque is going to be given by this PID controller. So the PID controller, we have to have this theta sub E. Theta sub E means that you have to have some measurement of the error. And measurement of the error is typically possible in a robot because all the joints, you have these motors and there are encoders on those motors so that you know the angle, that it is at 87 degrees or 105 degrees. So that information is given to you by the encoders on the motors. So from that we can compute this theta sub E, which is the difference between the desired angle and the actual angle.
Is that reliable enough in practice?
Yeah. So this is, and of course, this is for one joint. So I'm doing the baby case. When you have many joints, you just do this separately for every joint. So it's pretty done in a straightforward way. Okay. And so what this says is, so again, you can do simple-minded stuff. Suppose you did not have the integral term and you just had a proportional control, or so there are variations. We call this, there's a PID controller. You can have a PD controller. PD controller means that you don't have the I term. You can have a P controller, which means you don't have either the I or D term, right? You can have a PI controller, which is you just have a proportional and integral term. So all these variations are possible. So if you do a simple-minded version, you will have a situation quite similar to that cruise control on the car. You will get a little steady state error because you didn't put an integral term. Okay, and this is, you're not supposed to really read it in detail, but one can do the algebra and, I mean, people can do this stuff, right? So, okay, I'll skip this, but, okay. And then there is a version of this, which is, what about tracking a trajectory? Okay, so there's a terminology here. There's set point control. Set point means that for example, it could be that in this little one arm robot, I wanted it to go from being at like at -π/2 to 0. So it was going to go down, and I wanted to raise it to horizontal, right? That's an example. So that's set point control, meaning that you want to be in one place and you specify that and you want to stabilize there. So there you are, and often you shift the origin to be 0 at that place, and the goal is to just stay there, not change. Okay, then there can be trajectory control. So in trajectories, you want to move, your theta should change as a function of time in a certain way. You want to achieve that. But we have a physical system. That means that it cannot magically change from a theta of 90 degrees to at the next moment being 0 degrees. I mean, the laws of physics apply. So the dynamics of the system controls how you can evolve the system. So you have to apply your control law cognizant of the fact that these are physical objects which have to follow Newtonian dynamics, and we can write down the equations for that. So this creates, there's this whole game of trajectory optimization and so on, and designing control laws for that. Again, this kept our colleagues occupied in the past, and back in the 80s and 90s, all these things were worked out. So it's all there. You should read up about it. Okay. And I am going to, okay, I should give you a break at some point, but there is a, I'm not really going to go into this. So you okay. I want to give a little flavor of it, which is that essentially this class of controllers, which I call computed torque control or feedback linearization. Again, this is a topic which I'm really not going to explain, but the idea is that you actually do a combination of using the model, the feed-forward term. So let us assume that we know the dynamics. So knowing the dynamics means that you know the mass of the link and things like that, right? So for your known robot, you know the masses of the links. It's all there in the URDF file, and you incorporate that. So you don't assume that it's like all that is an unknown. And you also have a term which is measuring the error and feeding it back using the PID control. So you design a controller which has both of these aspects. And if you want, you can think of it as a combination of a feed forward and a feedback controller. The feed forward part deals with the known dynamics corresponding to the masses of the links and so on. And then there is always going to be unmodeled dynamics and disturbances. And your feedback loop is taking care of that. And so this is a very good design principle, and that's what this computed torque control is sort of a way of dealing with this properly. Okay, and there are variations on this theme. So I'm not going to go there. And this picture tries to give you examples. So here the goal was, so there is this bar linkage which was at 45 degrees and you wanted to go to 135 degrees. And there is a desired trajectory, and there is a simple, so over time, it does the right thing. But if there are errors, then the computed torque controller does better. So there are three controllers here. There's a FF, which is a feed forward controller, which doesn't have any mechanism for dealing with disturbances. You just assume that everything is correct, you do that. So that's like my first example for driving a car on the road. You just pick you have this, you pick a certain throttle angle, and that's it. So that's the pure feed forward. FF is for pure feed forward. Then you can design a controller which is based on just error measurement and doing the right thing. So that's the PID controller. And then there is this computed torque controller, which is a combination. You build in your prior knowledge, if you will. Okay, that's in the feed forward part, and yet you also measure the error and you correct on that. And the purpose of these two panels is to show that that works the best. And that's not surprising. I mean, it's intuitive that if you have prior knowledge, it should help. Okay. And at this point, I'll give you a break. So let's take a 10-minute break and resume at 4:15.